Good evening once again. For talk number 21 to Bromsgrove Astro. Yes, yeah. That's 21 in the last 10 years. So this, as you can see, is about the beginning of everything, about how the universe came to be. This is what we see at the moment, but where did it all come from is basically the big question. So here, taken a few years ago, is a digital sky survey. It looks a bit like a sort of a Disney animation of the universe, and it almost is, except that this is real. This is not so much just a fanciful animation. This is actually a 3D map of the universe around us. In other words, quite a few hundred million galaxies have been mapped out in terms of where they are in the sky and their distance. And hence, it is possible to effectively plot in 3D where all the local galaxies are. In this context, a billion is only local galaxies, because there are, of course, far more than that in the universe itself. But as we fly through, we can see that all of the galaxies in our neighborhood, at least, and probably elsewhere, are not uniformly distributed. There appear to be occasionally knots of superclusters of galaxies, lots of them in a small volume. Here's one, for instance, quite a few in a relatively small volume. And occasionally we see filaments that seem to join clusters together. And we can see quite a few of them here. And every once in a while we fly through a region which doesn't seem to have that many galaxies at all. So there appear to be large so-called voids, not truly empty, but rather sparsely populated with galaxies. So when we look around, when we look at the observable universe, we see loads of stuff out there. We see billions upon billions of galaxies, and we know that each of those galaxies probably has maybe a few 100 billion stars, and we now know that most of those stars have got solar systems going around them, so countless numbers of planets. But the question is, if that's what we see out there now, where did it all come from? That's the question we're trying to answer. The Hubble Deep Field, when it looked into the middle of nowhere, picked a blank bit of sky, and then exposed for basically about 10 days or so, it picked up, again, a huge number of galaxies. In this particular picture, there's about 3 individual stars. Every other dot is a galaxy. So the large orange blobs are quite definitely galaxies, but so are these small whitish or bluish dots in the background. They are all individual galaxies as well. So we know there's a huge amount of stuff out there, and part of the job of research telescopes is to look at what's out there and try to make sense of it all. But this question I'm trying to answer today is, where did it all come from? Where did all these galaxies come from? What were these galaxies like if we wind the clock back? So that's what I'm talking about, the creation of the universe. If we ask, when did it happen? We have a relatively precise answer. We know that the universe was created 13.77, let's call it 13.8 billion years ago. We know that fairly accurately. How long did it take to make a universe? Roughly speaking, it takes 3 minutes to make a universe, and I'll show you why 3 minutes in due course. Where did it happen? That's a common misconception. A lot of people ask, where was the Big Bang? Was it over there or over there? Nope. The Big Bang was the creation of the universe, and therefore it happened everywhere. In other words, every point is equally valid in terms of where the Big Bang occurred. Why did the universe evolve the way it did from 13.8 billion years ago to what we see now? Because of the laws of physics. And I'm a physicist, so I believe that is all correct. We may be missing some of the facts here or there, but the laws of physics tell us how the universe came from creation to the point we are today. And how do we know all that? Well, that evolution is based on the laws of physics, and we know that to be true, or at least as close to true as any scientist can say is true, again, based on our understanding of the laws of physics. Just a few comments about nature and how we look at the universe. Nature is not repetitive. If nature was repetitive, it would be really, really boring. If the same things happened over and over and over again, may seem like that some days, but no, if everything just happened repeatedly, it would be very easy to predict what happens next, but life would be really, really boring. But nature is not unpredictable either. Again, when you talk to some people, that's a little difficult to comprehend, but nature is not unpredictable in the sense that we cannot make any prediction about what's going to happen tomorrow. For instance, we can predict that the sun is going to rise tomorrow. We may not see it, depending on Storm Dennis and other things, but we know the sun is going to rise tomorrow. Nature is not unpredictable. If it was unpredictable, we wouldn't be able to make any sense of the world whatsoever. We would never be able to say, based on our understanding now, this is what we think is going to happen tomorrow or next year or in the next 1,000 years or in the next million years. So nature is not repetitive and it's not unpredictable. It's somewhere in the middle, i.e. it's interesting. And that's one of the reasons physicists study nature and astronomers study the universe in general. But how does it work? How do we know how the universe works? How can we tell how the universe works, given that we can't watch it evolve over 13.8 billion years? One way of thinking about this is not to talk about the laws of physics, but just to say the universe behaves a particular way. What are the rules that govern the way the universe works? What are the rules of the game? If we were thinking about chess, can you work out the rules of chess by just looking at that picture? That one picture on its own, if you already know the rules, that might make sense to you. But if you don't know the rules of chess, if you show that picture to somebody who's never seen the game of chess, they would not be able to make sense of what's going on. They might just about be able to tell that one set of pieces is slightly silvery and the other set of pieces is slightly goldy, and they all seem to have very peculiar shapes, and some shapes reproduce on the two sides, and others don't. One appears to have fallen over. But in terms of where they're positioned and how you play the game, you can't tell the rules from that picture. How do you tell what's going on with chess? Well, you read the manual. Okay, that's one option. There is no operating manual for the universe, so we can't just read how the universe works by genning up from a PDF file. If we were trying to work out how chess is played out, we might watch not a single picture, but a movie. And if we watched a movie of two people playing chess, how they start, how they move the pieces, what happens when one piece takes another piece, then we can start to build up an idea of what the rules of the game actually are. But looking at one game is probably not enough. But if we watched two players play 1,000 games, then we would get a pretty good idea of what the rules of chess must be in order to play out the way they do. But we can't do that with the universe, in the sense that if we look at that galaxy, we can't decide to, rather than take a picture, we can't take a video of that and sit and watch it and see how this galaxy revolves and see how it changes and see how the stars come and go, how stars are born, how stars die. If we look at that same galaxy tomorrow, it will look pretty much the same. Look at it in another 100 years, it will look pretty much the same. Perhaps one or two supernova, and maybe the occasional nova, may actually change, but on the whole, the galaxy will look the same. It's very difficult to tell how things evolve just by staring at them. And so, unlike the game of chess, we can't watch a video of the game being played. But the alternative is, instead of watching a video of people playing the chess game, we could take snapshots of 1 million different people playing chess and look at where the pieces could possibly be, not in 1 million videos, but in 1 million individual still pictures. If we took 100 games all going on at random and took a picture of each of them, we could start to build up an idea of what must the rules have been to allow the chess pieces to end up in this configuration, and that one, and that one, and that one, 1 million times over. It's not good enough to look at a dozen, but if we had 1 million of them, we might get an idea of the rules of chess. And that's what we do with astronomy. We don't look at one galaxy and try and work out how the universe came to be. We look at a large number of galaxies. And if we have enough of them, okay, here there's only a few thousand in a Hubble picture, but we have other survey telescopes which are looking at galaxies that's produced, for instance, the Sloan survey that I showed in the opening sequence there. So we do have an idea of where millions, if not billions, of galaxies are. We don't necessarily understand all of the evolution of those galaxies, but we do have a picture of a very large number of galaxies. And if we want to understand how the universe came to be and how all these galaxies came into existence, we have to explain how it is that we can end up with a picture like that, with some galaxies that are apparently different sizes, some galaxies that are different colors, etc. And that's how we deduce the rules of the game. We look at as many examples as possible by looking in all directions of the sky and trying to figure out what all the stars and all the galaxies are doing, not in terms necessarily of their motion now, but in terms of what the snapshot looks like. How complex must the rules of the game be? In order to create a universe that is as complex as the one we see. Most of us have telescopes. We look out and we see enormous numbers of stars and nebulae and planets and galaxies. Here's a picture not taken by me, just stolen off the internet, a picture of the Orion region. We can see the Horsehead Nebula in the bottom left. The Orion Nebula is off to the top right. How complex must the rules be in order to explain how you can go from something to something as complex as that? How complex is that, and how can we possibly write down in any form whatsoever, mathematical or otherwise, the rules that dictate that is how that came to be? Just because what we're looking at is complex doesn't mean the rules that generated that structure are necessarily complex. For instance, if we take a mathematical set of points, these are simply colored pixels generated by a particular mathematical formula that were discovered by the mathematician Mandelbrot. If we have a little look at the detail, we see that there's lots of pixels there, each colored according to a mathematical formula. And if we zoom into this set of colored pixels, we find that this set of colored pixels is, in a sense, infinitely complex. If we zoom in, we start to see motifs which look a little bit familiar. But they are familiar, but they don't actually ever repeat. Just like one person might look a little bit similar to another person because they both have a head, 2 arms, 2 legs, etc., but they're not actually quite the same. So when we zoom in, we see lots of structure, lots of detail, and the more we zoom in, the more detail we see in this particular mathematical set of colored dots. But it never actually repeats. We see something that looks like a little bit of a sort of a horse head or maybe a seahorse or something like that. And we get the feeling that we've seen that before, but when it's checked, no, this never actually repeats. The more we zoom in, the more detail we see. How complex must the mathematical formula be that generates the entire set? Not just the little bit of the set we're looking at, but the entire infinity of as much detail as we would like to zoom into. And I've already zoomed in by probably more than 1 million-fold. I'm probably zooming in towards 1 billion-fold now. We've zoomed in the equivalent of zooming in from the size of the universe down to something smaller than our galaxy, possibly zoomed in to the point where we're now zooming into our solar system. And still we see detail, and still the detail is there, all from one formula. So how complex must that formula be to generate anything as infinitely intricate as that? Well, the answer is that's the formula. That's the formula that Mandelbrot discovered. If you apply that formula over and over again, you can decide how to color these dots, and you end up with a mathematical set of points, pixels if you will, that is infinitely complex. The point being, just because something looks very complicated doesn't mean the rules that generated that particular structure are complex. Complex does not mean incomprehensible. Just because something is very complex, that might make it difficult to understand, but it doesn't necessarily mean it's difficult to understand. Einstein had this wonderful quote: "The universe is extremely complex, but the most incomprehensible thing about the world," universe if you prefer, "is that it is comprehensible." If we think about it, we can figure out what the rules of the game are. Even though the universe is mind-bogglingly big, with a huge number of stars and galaxies out there, that doesn't mean that we can't understand it based on a few rules, i.e. a few laws of physics. So what's the flow of thought that takes us from looking at the universe to try and understand where the universe came from? Well, we have the observation that when we look at the galaxies, especially the more distant galaxies rather than the ones that are right next door to us, when we look at the galaxies, they all seem to be moving away from us. So if the galaxies are moving away from each other, we come to the conclusion the universe is expanding. Okay, that's one observation and one conclusion about that observation. But we have to bolster that with the fact that not only do we look at the universe, we try and do experiments on Earth to try and understand how stuff is put together, how matter exists, what atoms are, for instance, and what atoms are made of. We are made of molecules, molecules are made of atoms are made of something or other. How do we figure out what atoms are made of? Because presumably the rest of the universe is made of those same atoms. So we need to understand what's going on Earth before we can understand what's going on in the rest of the universe. So we make observations, particle physics experiments, for instance, the Large Hadron Collider. We bang stuff together, see what happens, and that gives us an idea of what matter is made of. But along the way, we have to make an assumption. This comes back to nature being either predictable or unpredictable. If we assume the laws of physics keep changing, if we assume that we can do an experiment and understand something about this atom, but tomorrow it's going to be different and the rules have changed, then there's no way we can ever get any understanding of the universe around us. If the laws of physics keep changing, and what happened yesterday is not going to be the same as tomorrow in terms of the rules that decide what happens, if the laws of physics keep changing, then we're not going to make any progress. We also have to assume that the laws of physics are not only immutable in time, but they're the same for everybody, truly universal. In other words, if there is a set of laws of physics, it applies to me just as well as it applies to you, just as well as it applies to anybody standing on the planet Mercury, or anybody at Alpha Centauri, or anybody in the Andromeda Galaxy, or anybody elsewhere in the universe. If we don't assume the same rules apply to everybody, and the rules only apply to us, we can't make any progress in understanding how the universe is put together. So we can't prove that, but we have to assume that to make any progress whatsoever, that the laws of physics don't change with time and don't change with your position in the universe. They're the same for everybody. They were the same a million years ago, and they will be the same a million years hence. That doesn't mean our understanding doesn't change, but we don't believe the laws themselves, as we understand them, change. So what do we get if we take those observations and those assumptions? We come to the conclusion that the universe must have been born 13.8 billion years ago to explain the expansion that we see, and it must have been very hot in those early days and expanded, because that's what the laws of physics tell us about expanding systems. As they expand, they cool. So if it's a certain temperature now, it must have been a lot hotter in the past. It was born very hot, and it's been expanding and cooling ever since. So the big question, where did all of the matter that we see today, all of the matter in the observable universe, all of those billions of stars inside all of those billions of galaxies, where did all that stuff come from? If we believe the laws of physics tell us where things come from, how far back in time can we go and still reliably say, yep, I'm pretty confident that the laws of physics would still apply? Physicists are fairly arrogant people, and they sort of say they always apply, but the question is, at what point does our understanding start to crumble? How far back in time can we go before we effectively say, well, we don't really know, as Patrick Moore would say, as opposed to, yeah, we know what's going on at that point. When we look back over 13.8 billion years, if that's when it started, how far back down to that 13.8 billion years can we go? Are we happy that in the first million years of the creation of the universe, we understand what the laws of physics were telling us? Yep, no problem at all. Can we go back to the first 1,000 years out of those 13.8 billion years? Yes. Can we go back to the first year after the Big Bang and say, yep, we pretty much know what was happening in those first 1,000 years? Yes. Can we go back to the first 24 hours? I know these times don't really mean much when we haven't got an Earth spinning, but a day in the conventional sense of 24 hours as we understand them at the moment. If we go back to the first day after the Big Bang, are we confident that the laws of physics are as we would understand them today? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second of the 13.8 billion years? Yes. What about the first millisecond? Yes. What about the first microsecond? What about the first millionth of a second after the Big Bang? Do we know what was going on? Yes. What about the first nanosecond? Billionth of a second? Yes. What about the first trillionth of a second? The first picosecond after the Big Bang? Not really. No. That is where we draw a line in the sand and say, even arrogant physicists don't claim to understand what was going on in the first picosecond after the Big Bang. So the first trillionth of a second, 11 noughts, then a 1 on the end, 0.11 noughts 1. After a picosecond, we understand what was going on. Before the first picosecond, we are on somewhat shaky ground. We can come up with theories quite happily. you can say this person has come up with a theory of what's going on in the first fraction of a second. We can't prove it and we can't disprove it, therefore it's purely a theory. After a picosecond, everything after 1 picosecond is relatively well understood. That might sound rather incredible and very arrogant to say, but this is the statement. After 1 picosecond, 1 trillionth of a second after the Big Bang, everything since then has played out the way you would expect from the laws of physics that we understand today. And therefore we think we've got it right. That was a very long introduction to what I'm talking about, because I wanted to lay down what it is we're doing and what we're approaching, this rather big question of it's all out there, where did it all come from? So I've spent quite a few minutes just laying the groundwork of what it is I'm talking about. I'm going to cover 1 or 2 basic ideas before talking about what happened in the first fraction of a second. Then I will move on to the first few seconds. Then I will move on to the first few minutes. I won't continue at this speed for 13.8 billion years because that will take a little while. I'll then jump 377,000 years, not an arbitrary number, a very specific number. We'll jump 377,000 years from the Big Bang because something very important happened at that point. And then I'll cover the next 13.8 billion years in brief. Okay, rather faster pace, as it were, because Sue won't let me speak for more than 3 hours. So that's what we're going to do in this particular talk. So firstly, a few basic ideas. Apologies if you know this, but some of this you will know, some of this you might not know. We are made of atoms. I'm sort of assuming everybody is comfortable with that idea. We are made of molecules. Molecules are made of atoms. Atoms have been known about for more than 100 years now, and therefore most people are comfortable with the idea that we have building blocks which make up pretty much everything. An atom is in a sense a complex object, but we can think of it simply as a nucleus of stuff. It happens to be positively charged electrical stuff, and buzzing around it a whole load of electrons, negatively charged stuff buzzing around them. So we are made of atoms, and an atom is made of a nucleus and a whole load of electrons. To the best of our understanding, electrons aren't made of anything, in the sense that you can't take an electron, cut it in half, and have a look inside to see what it's made of. As far as we know, an electron is a fundamental particle. Fundamental meaning you can't subdivide it into anything else. Okay, we might be wrong on that, and in 100 years' time we might have to revise that idea, but at the moment we think electrons are fundamental. Nucleus, by definition, is actually quite not a fundamental particle. It is definitely something that's made up of other stuff. That was discovered, again, best part of 100 years ago, back in the early part of last century. So we know the nucleus of an atom is made up of 2 types of particles. I'm going to throw a few words at you. It doesn't really matter what those words are as long as you understand the basic idea. A nucleus is made of stuff. We call them protons and neutrons. Protons have got a charge. Neutrons don't have a charge. So protons repel each other because they're all positively charged. Neutrons don't have a charge. But protons and neutrons are not fundamental either. They are not fundamental in the sense that we can cut them and open them and find out what's inside. And when we do that, we find that protons and neutrons are both made of stuff with a stupid name called quarks, or quarks, depending on if you're English or American. So protons are made of 3 quarks. What is a quark? It doesn't matter. It's a fundamental particle, and as far as we know, you can't take a quark, cut it in half, and see what's inside of it. So to the best of our knowledge, quarks are individual particles which make up a proton. They also make up neutrons. A different combination of quarks will make a neutron. Protons and neutrons together make up a nucleus. A nucleus, when it's got a load of electrons buzzing around it, is an atom. Atoms collect together to make molecules. Molecules collect together to make you, effectively, and other animals and other biology. So that's a sort of hierarchy, if you like. And they were discovered in that order because we knew about atoms, and then we discovered that atoms were made of other stuff, like a nucleus. And then we discovered that the nucleus was made of protons and neutrons. And then we discovered that protons are made of quarks. So our discovery, our understanding of the micro world went in that direction because it takes more and more energy to split things apart. It takes a small amount of energy to take a molecule and to divide it into its atoms. It takes more energy to take an atom and to split the atom into nuclei and electrons. It takes a huge amount of energy to take a nucleus and split it into protons and neutrons. It takes an enormous amount of energy, like the Large Hadron Collider, to take a proton and split it up into its constituent quarks. So more and more energy is required to split things as we go down that sort of, it's a bit like having a Russian doll idea. The more you look, the more energy you apply, the more you open up the Russian doll and find there's another one inside. Okay? So it doesn't matter what words we use as long as you understand those concepts. And if we're going from low energy to high energy, physicists talk sometimes about energy and sometimes about temperature. Something that's cold has got a low amount of energy, a small amount of energy. Something that's hot has got a large amount of energy. So low energy to high energy is the same thing as cold at the top and hot at the bottom. But remember what we said about the universe. We believe it started hot and is now cooling down. So the universe is not traveling in the blue arrow direction. The universe started hot and is going cold. So the universe, or time if you like, is running upwards. The universe wasn't built from the top down. The universe was built from the bottom up. The universe starts with a whole load of particles, and as time goes by, eventually those protons start to combine with neutrons to make a nucleus. And as time goes by and the temperatures start to drop, eventually the nucleus will start collecting electrons and make atoms, and eventually those atoms will make molecules. So because the universe started hot and is cooling down, the universe is going from the bottom up, from fundamental particles which then join together, which then join together, which then join together to make more and more and more complex structures, starting with simple particles and building through atoms to us and stars and galaxies. So let us start our journey of where did things actually begin. T equals 0, the instant of the Big Bang. It's perhaps disappointing, but if you ask the question, what happened at the instant of t equals 0, then we have to remind ourselves that we cannot provide a definitive answer. The laws of physics, as we understand them at the moment, the rules of the game that we think apply, we don't think those rules of the game necessarily apply before the first picosecond. So we cannot definitively say what happened at t equals 0. There's plenty of people who say it might be this, it might be that. Fine, yes, there's lots of theories. None of them can actually be proved. It might be, and this is one of the, I was about to say common, this is one of the widely held beliefs, that the universe was born from a quantum fluctuation. Quantum mechanics is really weird. Quantum mechanics describes how things happen on a really small scale. But we have been studying things on a really small scale for quite a while. We've been studying atoms and nuclei and fundamental particles. We've been doing that for a century. So we sort of got a handle on what quantum mechanics is telling us about really, really small things. And it is possible to borrow from nothing. Perhaps you were told at school that energy comes from one place and goes to another place, but you can never get energy from nothing. Unfortunately, that's not true. Quantum mechanics says you can do that. You can borrow energy from nothing. It's like borrowing money from a non-existent bank. It can just appear in your hand, and you can get it from nothing. The catch is you have to pay it back. So it is weird that you can borrow from nothing, and yes, it sounds weird, but quantum mechanics is weird, and that's a different talk, okay? So you're going to have to take it on trust that physicists know how quantum mechanics works. That's not the same thing as understanding why quantum mechanics works, but having studied atoms for a long, long, long time, not only do we understand quantum mechanics to the point of understanding fundamental particles, we've even built microscopes that work on quantum principles, and they show us what's going on at high magnification. So it's not just a question of understanding. We've actually built things that work on the principles of quantum mechanics. So we believe it's right. How much can you borrow? So you can borrow money from a non-existent bank and the money's in your hand, but you have to pay it back. And not surprisingly, it works like money. If you borrow a small amount, well, the interest grows relatively slowly, and you can pay it back at your leisure. If you borrow a very large amount of money, of course, the interest grows very rapidly, and you have to pay it back very quickly, unless you want an enormous debt. It's the same with energy. If you want to borrow energy from nothing, how long can you borrow it for? Well, the product of one times the other has a limit. It's a fundamental limit. Nobody understands why the universe has imposed this limit, but the limit apparently exists. You can borrow as much energy as you like, but the length of time you've got to pay it back again is determined by one times the other has got a limit. So in other words, you can borrow a lot of energy for a very short time, or a very small amount of energy, and you've got a lot longer to pay it back. Why is that relevant? Well, because it's really weird, but if you look at the total energy of the universe, all of the matter is positive energy, E equals mc squared. All of the gravitational energy in the universe is negative, because as you bring two bodies together, you get a negative energy. They fall together, if you like. And when people have done a very rough estimate of all the positive energy and all the negative energy in the universe and added it all up, what does it come to? Roughly zero. So if you're limited by one times the other has got a limit, if the first thing is zero, you've actually borrowed no energy in that sense. And so the universe is not that fussed about you paying it back. It's like borrowing energy and then the universe doesn't notice, and then you're allowed to keep it, and there's your universe expanding and cooling and producing Homo sapiens, which then start discussing it. So it is a really weird concept, and it might not be right. It is our understanding, based on our understanding of quantum mechanics and very small things. We know you can borrow as long as you pay it back. Maybe that's how the universe got started. It borrowed and it hasn't paid it back, because the total energy might be around zero, or at least a very small number. That is a hypothesis. It has not been proven that that is the case. Now let's move on a little bit. We are now moving forward a long, long time, and this is the time we're now dealing with. T equals 10 to the minus 35 seconds. At this point, 10 to the minus 35 seconds, the universe has expanded to be about that big. The universe is now a few centimeters across. It's about the size of a golf ball. And just like a golf ball, it's not perfectly smooth. It's a sphere, but it's not perfectly smooth. It's got dimples in it. And by the universe, I mean everything that we now see in the observable universe, all of those 100 billion galaxies, which contain each 100 billion stars, all of that stuff used to be inside that volume. Quite dense. The entire observable universe used to be inside a sphere a few centimeters in size. And if that doesn't blow your mind, you're either asleep or you're not listening. Trying to understand what black holes are doing is bad enough. Trying to understand quantum mechanics is bad enough. But trying to understand that the universe at one time used to be that size, and everything in the observable universe that we see, all the matter, used to be inside here. Not in the same way. It's not like all the galaxies were really small. It means all of the stuff that make up those galaxies have been compressed down to something of a ridiculous size. I invite you to pass this round, stick it in the palm of your hand, and just consider that that's what the universe used to be. By all means, pass it round. And
say I'm godlike.
Yes, if you like. If you want to feel like a god, please do, yeah. That's a pretty good representation of the universe, except that the universe didn't have the University of Liverpool logo imprinted on the side of it. I am fairly sure about that. It's more like that one. So the dimples are an analogy. The dimples aren't real dimples. The dimples are variations in density. It wasn't perfectly smooth in the sense of the same density everywhere. There were tiny variations in density when that golf ball was formed. How do we know that? Because that's the only way we can explain, as the universe got bigger, that we ended up with galaxies. If the universe was totally smooth, it would still be totally smooth. So because now we see galaxies over here and galaxies over there and a supercluster here and a void over there, there must have been some variation in the very early days to produce that. So those dimples, those variations in density of the very early universe, gave rise to the variations in density that we now call superclusters of galaxies or individual stars. So that's how we believe that actually occurred at the time of 10 to the minus 35 seconds. Remember, we still haven't got to a picosecond, so we're still not sure. But we believe that must have been the case, because how else could you end up with a universe that looks the way it does? We're not absolutely convinced about the rules of the game, but the only way we can explain the current universe is if it used to be the size of a golf ball with dimples in it. Let's move forward. We are now at a picosecond. Now we are on solid ground. Now the universe is a bit bigger. The universe is about the size of the solar system. Okay, the solar system doesn't exist yet. We're still talking about a soup of particles. Basically, a lot of particles have been generated, and it's still, roughly speaking, a sphere, but it's now what we would now call the size of the solar system, even though the solar system doesn't yet exist. And the temperature is now quite a balmy 10 to the 15 Kelvin. So what's that? That's 1,000 million Kelvin. Very hot still, even though the universe has now expanded from a point to something the size of the solar system, and it started to cool off. It's still extremely hot. And it's made of fundamental particles. Our understanding of fundamental particles are that electrons are fundamental, and quarks are fundamental, and nothing else is. So we believe that everything in that particular sphere, that soup of particles, was quarks and electrons. There weren't any protons, there weren't any neutrons, there weren't any atoms, there weren't any molecules. Way before we're getting to the point of making stars and galaxies, we think it was just a soup, literally just a combination of a very large number of quarks. A number so large, there's no point in me actually quoting what the number is. Very large number of particles, which ultimately will make everything in the universe that we see. The energy that we're talking about, the energy of the individual particles in this soup that now occupies the equivalent of a solar system, the energy of these particles is roughly speaking the same as the energy we can create in the Large Hadron Collider. When we bang particles together and see what happens, how much energy can we provide to two particles when we collide them in a particle collider? That energy is, roughly speaking, the energy with which the universe had lots of individual particles at 1 picosecond. And that is why everything from this point on is testable. Everything after this point, from 1 picosecond onwards, the amount of energy the particles have is the amount of energy we can give them in a particle accelerator, and hence we can test anything we wish beyond this point. Beyond this point, the universe is going to continue to expand and continue to cool, so the particles are going to lose energy, and those energies we can reproduce in the laboratory. Okay, not many laboratories, but the Large Hadron Collider is one in which we can reproduce that. And hence, everything from here on is testable. And that is the bottom line for physics. It's all just theory unless you build a theory which produces predictions which you can test. And if we can test them in a particle collider or some other laboratory, then they're not just pie-in-the-sky theories, they are testable structures that we can actually use to try and understand the universe. Energy and matter are continually changing backwards and forwards. Matter and antimatter. Matter is what you're made of. Antimatter is the opposite. It's, for instance, an electron buzzing around an atom in your body is negatively charged. But there's an equivalent particle which has all the same properties, the same mass, but it's positively charged. We call that an anti-electron. Similarly, there's anti-quarks. A quark has a particular set of properties. There's a particle with, if you like, the mirror image of that, called an antiparticle. We know about antimatter. There's not much of it around. We can generate it in the laboratory, not quite in the way you might have read in Angels and Demons, if you've got any Dan Brown fans, but antimatter does exist. Again, not on the scale of the matter-antimatter engines in the USS Enterprise in Star Trek, but antimatter does exist. And when you take a certain amount of energy and feed it into E equals mc squared, you can calculate that energy can create a whole load of matter and a whole load of antimatter. In the early days, what was energy creating? Was it creating quarks or electrons? Well, probably a mixture of quarks and a mixture of electrons, but it doesn't actually matter. It matters a lot to the particle physicists because that's what they spend all their time studying. But to me, it doesn't matter. All that matters is energy made some amount of matter and its opposite. So for instance, it made, well, probably not tangerines and anti-tangerines, but it made stuff and anti-stuff. And they are equal and opposite, so just like the engines on the Enterprise, they will annihilate each other and you'll end up with energy again. So the big E is just my way of representing energy because I don't know how else to draw it on a diagram. And that energy will, a fraction of a second later, generate more matter and antimatter. Not necessarily the same stuff again. It might generate a quark and an antiquark. They might annihilate, goes back to energy again, and then that energy might create an electron and an anti-electron. It might generate some other type of matter. Again, probably not a hot dog and an anti-hot dog, but it doesn't matter. It just generates stuff and anti-stuff. And the matter and antimatter are converted back to energy, which makes more matter and antimatter, which makes more... It goes backwards and forwards and backwards and forwards. Over and over again, matter and energy are being converted back and forth according to E equals mc squared. And then here's one of the quandaries of modern science is somehow, in a way that we really don't understand, matter got a foothold over antimatter. According to the rules, whenever energy makes matter and antimatter, you should generate the same amount of stuff in both cases, the same amount of matter as antimatter. If you generate 1 kilogram of matter, you should generate 1 kilogram of antimatter. But in the early universe, somehow, matter gained a slight excess. In other words, we generated a certain amount of matter and a certain amount of antimatter, and they didn't quite match. Here I've shown one is 10% more than the other. It wasn't that dramatic. The difference between how much matter and how much antimatter was not 1 part in 10, it was more like 1 part in a billion, but there was still a quite definite excess. So this matter could annihilate with that antimatter, and this matter could annihilate with that antimatter, and all of those will annihilate and produce energy. Ultimately, energy in this context means light, radiation, gamma rays or X-rays or visible light. And so you've got, because you've got an excess of matter over antimatter, that last tangerine at the end hasn't got another tangerine to annihilate with, so it's left as floating around as matter. So in other words, you end up with a universe which is full of light and radiation and a tiny amount of matter. 1 part in a billion of the original matter, 999 million parts out of that billion have annihilated, and we're left with 1 part in a billion, and it's just as well because all of that energy is basically just light, and that tangerine left over is all the matter in the universe, i.e. you, me, the Earth, the solar system, the Milky Way, the Andromeda galaxy, every galaxy we can see. As far as we can tell, none of the galaxies out there are made of antimatter. We've done very careful tests by looking at very carefully at various galaxies, looking for signs of could they possibly be made of antimatter? And the answer appears to be no. As far as we can tell, the entire observable universe seems to be made mainly of matter. The amount of antimatter that's floating around is tiny. We can generate it in the laboratory. Some radioactive decays do produce antimatter, but very, very small amounts. So we're glad that there was an imbalance. If that imbalance didn't occur, there would be no matter in the universe. The universe would be full of light and nothing else. It would just be light bouncing around the universe. There would be no stars, no galaxies. So we should be thankful that for some reason matter gained a slight excess over antimatter, and what's left is us. Let's move forward in time. We're now going to go to a millisecond, the first thousandth of a second. Still too short to really comprehend how long it is since the Big Bang, less than the blink of an eye. We're still talking about that fraction of a second. Matter and antimatter are continuing to pop into and out of existence. We still have energy creating matter and antimatter annihilating to produce energy, back and forth and back and forth. That dance continues for another fraction of a second. Protons and neutrons are made from 3 constituent quarks. So there's lots of quarks in this soup. let's forget the electrons for the time being. There's lots of quarks in this soup, and they're continually transforming into each other. We won't worry about the details, but 3 quarks can make a proton on the left-hand side, but also 3 quarks can make a neutron. And so neutrons can transform into protons, and protons can transform into neutrons, back and forth and back and forth and back and forth. Particle physicists insist on giving these quarks labels like red, green, and blue, which is nothing to do with color. It's just a convenient label. They're too small to see. We don't know what they are like, but we know they have certain properties. They have certain properties. Let's label these properties red, green, and blue, because we sort of know what that means. And some of them might be spinning this way, and some of them might be spinning that way. So let's call some of them up and some of them down. We don't have to worry about the details, but if we have 2 ups and a down, we call it a proton. If we have 2 downs and an up, we call it a neutron. So we don't have to understand what those properties are. We just have to understand there are different types of quark. And if they gather together in little sacks of 3, then if they gather in particular combinations, we call it a neutron. And if they gather together in a different combination, we call that a proton. We're now into the heady times of 1 second. Now it's almost comprehensible that we're talking about 1 second after the Big Bang. The universe is now cooled off to only about 1 billion Kelvin. So quite cool by comparison with the earlier temperatures. It's now so cold, remember that scale I showed, that the Russian doll means the more energy we apply, the more we can break these things apart. Now it's too cold for protons and neutrons to swap back and forth. If we give them enough energy, they can do that. But now the universe is so cold, being only 1 billion Kelvin hot, there's not enough energy for protons to readily change into neutrons back and forth. Protons are a little bit lighter than neutrons. Here I'm labeling protons as little red spheres and neutrons as little blue spheres. Neutrons are a little bit heavier than protons. How do we know that? Because we measure it in the laboratory. And we assume that a proton on Earth is the same as a proton in Alpha Centauri, is the same as a proton in the Andromeda Galaxy, as well as anywhere else in the universe. So if protons are lighter than neutrons here on Earth, we assume that they have always been lighter than neutrons, and that's the same throughout the entire universe. So if protons are lighter, only by a little bit, 0.1%, so they're almost the same mass, almost the same weight, but slight difference, that means the universe makes more of the lighter one. This is a fairly fundamental principle. Given the choice of making heavy particles or light particles, the universe will always favor the lighter one. The lighter one being the lower energy or the lower mass. It's like saying, why does a ball roll downhill? A ball rolls downhill because the bottom of the hill is a lower energy than the top of the hill. Why does this laser pointer drop if I let go? Because the floor is a lower energy than the roof in this particular gravitational field. Given the choice, nature will always take the easy option and adopt the lowest energy state, or in the case of making particles, it will always produce the lowest masses. They're almost the same, so it doesn't produce all of one and none of the other. They are only slightly different, but that slight difference, which we can measure in the laboratory, we reckon ought to produce a ratio of 3/4 to 1/4. In the early universe, in the first 1 second of the universe, according to the rules of the game, according to the rules of physics that we understand today, the universe should have made 3/4 protons and 1/4 neutrons. That is a prediction based on what we understand. What happens if we move forward now a couple of minutes or so? So now we're talking about 100 or so seconds, or a few hundred seconds, 200 seconds. We know neutrons don't last forever. If you take a neutron, isolate it from anything, and stick it in the middle of nowhere and watch it, that neutron will spontaneously change into a proton. Neutrons, remember, are heavier. The neutron wants to become a proton because that's lighter. That's a lower energy state. Just like this laser pointer wants to fall, but I'm stopping it. If I let it go, that laser pointer will fall. If you take a neutron away from any other influence, that neutron will change into a proton. So neutrons, we call it unstable. We call it radioactive decay. But the neutron will change, or decay, into a proton. So the ratio changes from 3/4 to 1/4 of these representative 16 objects that I'm showing now we have 14 protons and 2 neutrons. That's the ratio that we have because some of the blue have changed into red. In this particular case, 2 blues have changed into a red because if we wait a few minutes, neutrons will change into protons if we give them enough energy. But after a while, they can no longer do that. In other words, once the universe has cooled down a little bit more, they are no longer able to do that. Now the universe is only 100 million Kelvin. That still might sound extremely hot, but to an astrophysicist, that is not particularly hot. Some stars, the core of some stars, not necessarily our sun, but some big stars might have a core temperature of about 100 million Kelvin. So we're no longer at the point of ridiculous temperatures. We're now at the level of temperatures that occur inside stars that might be only a few light years away from us. The universe is now cool enough that protons and neutrons can get together. Again, the Russian doll. We've been building up from the bottom upwards. Quarks have made protons, quarks have made neutrons. The universe is now cold enough for protons and neutrons to stick together. Earlier, the universe was too hot and they kept getting ripped apart again. Because remember, it takes more and more energy to rip things apart. When the universe was hot, protons and neutrons couldn't stick together. But now the universe has cooled off a little bit. When protons and neutrons get together, they can stick because they're no longer being ripped apart by the very high energies of the early universe. So after 2 or 3 minutes, it is possible for the nuclei to start getting together. Sorry, for the protons and neutrons to start getting together and forming nuclei. How do they group up? We've got far more reds than blues. So if you think of them as male and female, they can't all pair up and marry one of the opposite type. But we know that 2 protons would really like to get together with 2 neutrons because in the laboratory we look at how it works with nuclei of atoms, and when we look at the nucleus of helium, which is 2 protons and 2 neutrons, we find that is a very, very stable structure. In other words, it takes a lot of energy to tear 2 protons and 2 neutrons apart. It is a very stable structure. So 2 protons and 2 neutrons really want to get together, but that leaves us with 12 bachelors who've got no neutrons to hook up with because there's an excess of protons over neutrons because the protons were lighter. So what we end up with is a nucleus of a helium atom, 2 protons and 2 neutrons. The 2 protons, the 2 tells us it's helium because helium has an atomic number of 2. And we're left with a whole load of loose bachelors. These 12 protons don't have a neutron to hook up with, and they ultimately are just the nucleus of a hydrogen atom. A single proton is the nucleus of a hydrogen atom. Eventually, they will find electrons and they will form atoms. But now we have a whole load of nuclei of hydrogen and a nucleus of helium. And that's it. The universe is now done, pretty much. After 3 minutes, the relative abundance, how much hydrogen are we going to generate in the universe? How much helium are we going to generate in the universe? After 3 minutes, it's decided. From here on, the universe is too cold to actually change that ratio. The ratio has been decided by the amount of energy they've had up till now to form these bonds and form these structures. So if we look at that, what we should find is that we have, in terms of counting circles, we should have 12 heliums for 12 hydrogens for 4 heliums in terms of how many objects do we have. In other words, each of these is roughly the same mass, a neutron and a proton. So in terms of mass, in terms of kilograms, what should we see if we look out into the universe? We should see 3/4 of the universe is hydrogen and 1/4 of the universe should be helium. If we've got the rules of the game right, if we understand the rules of physics, if we understand how the universe came to be, if we understand those first 3 minutes, then the universe should have made 3/4 hydrogen and 1/4 helium. When we look at what's out there, what do we see? We see 3/4 hydrogen, 1/4 helium. That is why we believe this is the correct story. If this prediction wasn't borne out by what we see when we look at the amount of gas that's out there, then something is wrong with our understanding of physics. So over the last 100 years or so, this development of an idea of how the Big Bang happened and how that produced the hydrogen and helium, That has gone hand in hand with our observations of the universe and trying to tie in what is this predicting to what is it we actually see. You may say, yeah, but surely stars ultimately are processing helium. Our sun is using hydrogen as a fuel and generating helium, and other stars will be taking helium and generating carbon, and Betelgeuse will be taking carbon and trying to produce iron or something like that. So yes, the ratio will be changing, but surprisingly little. There was so much gas produced by the Big Bang that even though loads of stars are now processing all of these things and generating heavy elements, and thank heaven they did, because the heavy elements in your body came from a star at some point, an early generation star before our sun came to be. That's how you get the carbon, the nitrogen, the oxygen, the phosphorus, etc. that's in your body. But roughly speaking, all of the hydrogen and helium generated in the Big Bang is still out there somewhere. Only a tiny fraction of it has actually gone through stars and has been used to generate heavier elements. So the prediction of that much hydrogen with that much helium is one of the cornerstones of our belief that the Big Bang theory is the correct theory for explaining how the universe came to be. 3 minutes is all it took. The next 377,000 years were quite boring, because pretty much nothing else happened. For a third of a million years, the universe continues to expand and continues to cool. But effectively, nothing changes. That helium, that hydrogen, that ratio doesn't change. All that happens is the gas cloud, if you like, expands and cools. But something very important happens at 377,000 years. Eventually, after this length of time, the universe has cooled to a particular temperature. It's now cooled to about 3,000 Kelvin. That is important, because 3,000 Kelvin is what you need, the energy equivalent of heating something up to 3,000 Kelvin. If you took an object and heated it up to 3,000 Kelvin, it would be glowing white hot. That would be enough in any object we see around us to strip the atom and break the atom down. In other words, once the universe is colder than 3,000 Kelvin, it is possible for atoms to form. Up till now, a nucleus hadn't been able to hold on to an electron. There were loads of these nuclei around. The hydrogen and the helium nuclei are bouncing around. There's a whole load of electrons in this gas as well. But all of them are separate because the nucleus couldn't hang on to the electrons because they had too much energy. Just like a planet going around the sun, if you give that planet more energy, it goes flying out. That planet has to have a small amount of energy to keep it going round the sun. Give it too much energy, it'll fly away. Same with atoms. If you give an electron too much energy, the nucleus can't hang on to it. So once the universe has cooled to this particular point, it is now possible for a nucleus to hang on to its electrons from here on in. So now, for the first time, we have atoms. It takes 377,000 years after the Big Bang before you have atoms in the sense of a nucleus and electrons going round. Up to this point, you have positively charged nuclei, negatively charged electrons. We call that particular cloud a plasma. But what matters is once a nucleus hangs on to an electron and you get atoms, as soon as you get atoms, your gas is transparent. So for the first time in the universe's history, the universe is transparent. Up to this point, it's been an opaque mess. A whole load of nuclei, a whole load of electrons, a lot of light bouncing around, but the light couldn't go very far before bouncing off another nucleus or another electron. As soon as you have neutral, because positively charged nuclei and negatively charged electrons add up to nothing in terms of electric charge, as soon as you have an object with no electric charge, it's possible for light to go flying through this particular gas, just like the light from this screen is having to go through lots of atoms between the screen and you. There's a few trillion atoms, but that's not a problem for the light because all the atoms are uncharged because we have positive nucleus, negative electron. The light doesn't have any trouble whatsoever traveling through a gas if that gas is made of atoms rather than a plasma. And therefore, the universe becomes transparent. So for the first time in its history, it is possible for the light to be released. The light that up to this point has been bouncing around and rattling around like inside a pinball machine, bouncing off all of the positively and negatively charged particles, now the light is released. It's 3000 Kelvin, that's white hot. The universe would have been producing an enormous amount of visible light. Heat anything up to 3000 Kelvin, it will produce a lot of visible light. Some ultraviolet, some infrared, but mainly visible light, because the universe was white hot at this point. And we see that light because it was released after 377,000 years, and now we see that light, but it's been stretched out because since that point, 377,000 years, the universe has got a lot bigger since then. 13.8 billion years ago is when the light was released. Now the universe is 1,000 times bigger, which means the wavelength of the light has been stretched 1,000-fold. And what is 1,000 times longer in wavelength of visible light? If you take visible light and stretch it 1,000-fold, you end up with a radio wave, or perhaps a microwave. It ends up being a few centimeters rather than a little micron or so. Visible light has a wavelength of about a micron, 1,000th of a millimeter. Stretch it by 1,000, you end up with wavelengths of order millimeters or so. You end up with microwaves. And that is the cosmic microwave background. That is why that is sometimes described as the afterglow of the Big Bang, because it was the first point at which light was released from the Big Bang. For the first third of a million years, no light was released, but after that particular point, so-called the recombination era, where nuclei and electrons can combine to form atoms, then you end up with a whole load of microwaves. So it's difficult to see on the ground, but if you send up a satellite and look around the sky, you find the sky is bathed in microwave radiation. It's almost the same in every direction, except there's a little bit of stippling. There's a little bit, it's a little bit hotter here and a little bit colder there and a little bit hotter here and a little bit colder there. So the red and the blue indicate tiny differences. On the whole, it's the same temperature everywhere. The universe appears to be relatively uniform. But there do appear to be tiny variations in areas, in little blobs, that were just a little bit hotter and other areas that are a little bit colder. Remember the cosmic golf ball? The universe used to have dimples in it, and that was variations in density. And variations in density give rise to slight differences in the temperature of the microwaves that reach us, or the energy of the microwaves that reach us. And hence some bits of the universe appear to be ever so slightly warmer than other bits of the universe. Virtually all of it is about 3 Kelvin. Remember, it started at 3,000 Kelvin when the light was released. It's now 1,000 times bigger, so 1,000 times colder. So instead of 3,000 Kelvin, the universe is now about 3 Kelvin, i.e. pretty cold, but not absolute zero. It's a few degrees above absolute zero. And there is a small variation in different directions, which maps on pretty much to what we understand the original golf ball looked like. The golf ball had variations, and we see those same variations in the cosmic microwave background. So we see those variations, red and blue, in the previous diagram, and we believe that's what we're seeing, the dimples in the original golf ball. And that's why we would like to understand the cosmic microwave background better. It's not just an esoteric thing. It is fundamental to our understanding of how the universe was created. If we study that cosmic microwave background, we are effectively looking back to that first fraction of a million years after the Big Bang. Unfortunately, we can't go back to zero. We can only go back to the point at which the light was released, 377,000 years after the Big Bang. So let me just remind you of what our local neighborhood looks like. We live in the Milky Way galaxy. Not far away, we have the Andromeda galaxy, close enough to be able to see Nova, apparently, George, in this particular galaxy. And there's a few others in our so-called local group. There's the Triangulum galaxy M33, a similar sort of distance, and a few other rather unspectacular dwarf galaxies dotted around. If we go out a scale, then all of the local group is in this sort of central region here, and we start to see this structure that I showed you early on in the talk, that there are some regions that are quite definitely clustered. We have little knots. The so-called Virgo cluster here is a lot of galaxies concentrated into a relatively small volume here. and we sort of get this hint of a sort of a filament, a little chain of clusters that form, and other regions where there don't seem to be many galaxies at all. And if we go up to a larger scale, so that this whole region here, this filament we see running, roughly speaking, top right to bottom left, if we go to the point where that is now this little part of the Virgo supercluster, we find that there are lots of superclusters out there in the universe. And again, we see that there are quite definite clusters. There seem to be filaments, just like we saw in that fly-through video of the Sloan Digital Sky Survey, where we flew through and we saw clusters and we saw filaments. This is the same sort of picture. We can see filaments, and we can see areas that appear to be almost completely devoid of galaxies. There's one here, the Boötes void. There's one up there, the Capricornus void. And again, what we're seeing in the structure of the galaxies around us are effectively the dimples in the golf ball. Just like we look at the cosmic microwave background and we see variations, when we look at the density of galaxies around us, we see those same dimples in the golf ball. The dimples must have been there to explain why we get this particular structure when we look around us. This is the same sort of thing. This is a simulation where somebody has simply started with a large amount of matter in a cube and then calculated how that collapses, how the universe, as it expands, collapses into, by gravitational collapse, individual galaxies, clusters of galaxies, filaments, and voids. It's perhaps a little bit easier to see if we do that whilst it's rotating, and then we can see this sort of filamentary web, if you like, of the large-scale structure of the universe. We still have a little bit of work to do in terms of simulating how we start with a whole load of hydrogen. How do we end up with that particular structure? But generally speaking, all you need is a supercomputer and a bit of gravity and a little bit of time, and generally speaking, you can simulate what the universe actually looks like. And this is another simulation that was carried out at the turn of the millennium, and it's called the Millennium Simulation. As far as I know, they haven't necessarily improved on it. This is what a simulation shows of what you would expect the universe to look like if you start with a golf ball with dimples in it. What would you expect to happen if you left it alone for a few billion years? You would expect it, according to this simulation, according to our understanding of the rules of the game, according to the rules of physics, which in this case is pretty much just gravity, and give it enough time to do its job, then the universe collapses. It's still on a large scale, foamy, and the top right looks pretty much the same as the bottom left. In other words, the universe looks pretty much the same in any direction you look, but if you start zooming in, and if we take a video and actually zoom in, we see that that foamy structure, well, it's there if you're dealing with a scale of a billion parsecs or a few billion light years. If we start zooming in, we start to see that what we're actually getting are structures. Again, we're seeing individual filaments, we're seeing voids in some region, we're seeing filaments joining knots together, and we're zooming into this particular knot, which is a very dense part of the universe, which appears to be an enormous supercluster, and the more we zoom in, the more we can see individual clusters, and eventually perhaps individual galaxies if we zoom in far enough. So the simulation is not just a question of start with a lot of hydrogen and then let it collapse and see what happens, and I'll say why it's not quite that in the very last slide. But this particular simulation tells us that we think we've got the rules of physics just about right, in the sense that if we understand from our particle physics that we're generating lots of hydrogen and helium, and if we ask what happens to that hydrogen, the answer is it collapses and produces a foamy web, which is pretty much what we see when we look at where are the galaxies. We see the galaxies in knots, we see the filaments, we see this web structure, we see the voids. So the simulation appears to be very close to what the observable universe looks like. That's why we think we've got it right. The next 13.8 billion years, I said I would do that fairly briefly. The point is, 3 minutes gives you all the hydrogen you need. Once you've got hydrogen, that's pretty much it. Once you've got hydrogen, you can understand where galaxies come from, where stars come from, where planets come from. You can understand trees and mountains and snowflakes and rainbows and cats and... Okay, not cats. Nobody understands cats. But you can pretty much understand everything else. If you start with hydrogen, Everything else follows. Okay, it's very complicated as to what comes next, how you go from a cloud of hydrogen to a rainbow, but all of the physics is there. All of the physics we think we understand. It takes a few billion years and a lot of different steps, but essentially, if we start with hydrogen, there's no magic involved in starting with hydrogen after 3 minutes and getting to where we are now, cats notwithstanding. So there are still some details to be worked out, for sure. That's why people are doing astrophysics degrees or astrophysics research. But the big picture is, yep, we think the Big Bang is right, we understand where the hydrogen comes from, and our simulations tell us we would end up with filamentary structure with knots and filaments and voids, and that's what we see in the Hubble Deep Field or these surveys of galaxies. So we think it's right. Let's just remind ourselves of what the timeline was. It's a ridiculous timeline from 10 to the minus 35 seconds on this side to 13.8 billion years on the right-hand side. So we start very early on with a golf ball with dimples, i.e. variations in density across its volume. Eventually that will give rise to a soup of particles, which we might label red, green, blue, or up and down. It's a quark soup. There's loads of electrons in there as well, but for whatever reason people tend to call it a quark soup. So the universe is a whole load of an unimaginably large number of individual particles, all bouncing into each other, and eventually the universe is cold enough that some of them get together in threes to make protons and neutrons. That would happen after a fraction of a second. After a few seconds, those protons and neutrons will get together to make helium. What's left over is hydrogen. After a little while longer, the hydrogen and helium will mop up the electrons that are also in the soup, and after a fraction of a million years, atoms are made, light is released. That's when we see the cosmic microwave background. Nothing much happens after that. There's the dark ages, because it takes a while for stars to form. Stars only need hydrogen, gravity, and time. Well, they've got hydrogen, they've got gravity, you just have to wait a few million years before the stars switch on, and then you get to the end of the dark ages, and then stars and galaxies start to appear. So that's a very condensed timeline of what I've been talking about. So the jigsaw is still not quite complete. We're doing quite well. We've got the corners, the edges, the landscape. Bits of sky are still missing. There's still some bits of the jigsaw we don't understand. I've alluded to some of them already. Why did matter win over antimatter? As far as we can tell, it must have done, because we are here and we are matter, and there seems to be no antimatter apart from tiny amounts which we make in the lab or occur from radioactive decay. So at some point, it must have happened that matter got a foothold over antimatter, and we don't understand why, and we don't understand why it ended up as 1 part in a billion was the excess. We're happy that it was, because we wouldn't be here otherwise. What caused the asymmetry between the two? A lot of particle physicists are trying to understand that particular problem. I also said that all you need is hydrogen and gravity, and the system will collapse and produce filaments and clusters and voids and everything that we see. Well, yes, but only if we include dark matter. Dark matter is this weird stuff that causes galaxies to rotate at the wrong speed, but also we need to put dark matter into those calculations to explain how the hydrogen clouds collapse into filaments and clusters and voids. So yes, we can get the structures that we see, but not simply from the amount of matter that's out there. We must include a whole shed load of dark matter as well. And that's before we even think about asking what the hell is dark energy? Why is the universe not just expanding and slowing? Surely gravity will be slowing it down. No, the universe expansion seems to be speeding up. The universe is accelerating its expansion, and we don't understand why. So this talk is the beginning of everything, but I've tried to make it clear it's the beginning of everything that we see, everything in the observable universe, every star, every galaxy we look at. But that's not the whole universe, because that's only a tiny fraction of the universe. It's only about 4% of the universe is everything we see. Dark matter and dark energy account for the other 96%, which is still a bit of a mystery. We still don't know what dark matter is, and we haven't got a clue what dark energy is. But that's another story. Thank you very much.